The second factor is known as the electrophoretic effect. We are considering a negative ion. Suppose we have a negative ion in solution which is surrounded by positively charged ions, which is called the ionic atmosphere. Now when we apply electric field, the negative ion moves towards the positive electrode, but the ionic atmosphere, which is composed of positively charged ions, it will move towards the negative plate or negative electrode. As a result, as the negative ion is moving in the forward direction and the positive ions move to the opposite plate, then there will be a dragging effect. These ions will apply a drag on the negative ion while it is moving towards the positive electrode, and this drag of positive ions on the negative ion is known as electrophoretic effect. Now when we increase dilution, the number of positive ions which are dragging the negative ion in the reverse direction, in the backward direction, decrease. As a result, the negative ion is somewhat free and it can easily move towards the positive electrode, and the electrical conductivity as a result will increase. The third factor is known as the frictional resistance of the medium or viscosity of the liquid, viscosity of the medium. Let us suppose we have two electrodes, the negative electrode and the positive electrode, and we have ions, the negative ion and the positive ions, and these ions are present in a medium, in a solvent, and this solvent has a certain viscosity, which is the resistance to flow of a liquid. It resists the flow of a liquid. So when the ions move towards opposite electrodes through this medium, it offers a frictional force, offers a resistance to the flow of electron, and this resistance is known as frictional resistance of the medium. Now, based on these factors, a mathematical equation was proposed by Debye, Huckle and Ansager, and this mathematical equation is known as Debye-Huckle-Ansager equation. Debye-Huckle-Ansager equation can be mathematically written as lambda m is equal to lambda naught m minus 82.4 divided by square root of epsilon t into eta plus 8.20 times power 5 divided by epsilon t whole square root of epsilon t lambda naught m into c under root, where lambda m is molar conductance at certain dilution or certain concentration, lambda naught m is molar conductance at infinite dilution or at zero concentration when C is equal to 0. Epsilon is dielectric constant of the solvent, T is the absolute temperature, and C is molar concentration of the electrolyte, concentration in moles per decimeter cube. Now in this case, the first term 82.4 divided by square root of epsilon t into eta represents the electrophoretic effect, and if for a given solvent at a given temperature, this quantity always remains constant and it may be represented by A. The second term in the bracket, that is 8.20 times per 5 divided by epsilon t half, represents the asymmetric effect, and it will also be a constant for a given solvent at a given temperature, and it can be represented by B. Therefore, equation 1 can be written in the form lambda m is equal to lambda naught m minus A plus B lambda naught m square root of C. Now if we put the values of constants, if we are using aqueous solution in which we are using water, then at a given temperature of 25 degrees centigrade, then we know all the quantities. We know the dielectric constant of water, which is 80. We know the absolute temperature, which is 25 degrees centigrade or 298 Kelvin, and we know the viscosity of water, which is 72 dynes per centimeter. Now putting these values of constants, we get lambda m is equal to lambda naught m minus 60.2 plus 0.229 lambda naught m into C. If we plot a graph, if we change the concentration of solution, the molar conductance will also change. If we change the dilution of solution, the molar conductance will change. And if we plot a graph for 1,1 electrolyte, for example, 1,1 electrolytes are those electrolytes which produce univalent ions like sodium chloride or potassium nitrate. For 1,1 electrolyte size like sodium chloride, potassium nitrate, if we find out the molarity or molar concentration of solution, and if we determine the molar conductance of the electrolyte and we plot a graph, we get a straight line. However, it has been observed that this straight line curves, it deviates from the original trajectory at a concentration larger than 0.02 molar. Thus, Debye-Huckle-Onsager equation is applicable only up to a concentration limit of 0.02 molar and is not applicable. It is violated beyond this concentration. Allah Hafiz.